In this unit, we are going to talk about the matrices. We are going to see what is a matrix and what classes of matrices we have or know, and for this, simply knowing the operations between real numbers is enough. So we will start by remembering that a linear equation system has this expression that you see on the screen. X plus 3y plus 4z is equal to 2, 2x minus y minus 2z is equal to 9, x plus 10y plus 12z is equal to 5. And that when we try to solve this system using the Gauss method, it implies, for example, solving the system in this way. This here is what we are going to call a matrix. Let's say that we only use the coefficients of the unknowns, and these boxes of numbers is what we are going to call a matrix. Each row represents an equation, and each column is formed by the coefficients of the synchronics. Well, here the use of the matrices appears, although not only it appears here, it appears whenever we can build boxes of numbers. For example, if I have a country A with 3 international airports, A1, A2, A3, and a country B with 4 international airports, B1, B2, B3, and B4, and I relate all the flights that are joining each of the airports, well, from A1 to B1 there is a flight, from A1 to B3 there are 2 flights, from A2 there is one to B2, another to B3, and another to B4, and from A3 there is one to B4. Well, this is a form of representation by diagrams of Venn, which we could also represent as a box of numbers in this way. From A1 to B1 there is 1, from A1 to B2 there is none, from A1 to B3 there are 2 flights, from A1 to B4 there is 0, etc., etc. As you can see, again a box of numbers appears, which is what we are going to call a matrix. From there, the utility of the matrices, and they usually appear in the daily life. So, first, what is a matrix? We are going to call a matrix of order m times n to a set of m by n numbers arranged in m rows and columns. That is, m represents the number of rows I have, 1, 2, 3, 4. So to m and n represents the number of columns, 1, 2, 3, 4, so to n. The subindex of the elements of the matrix indicates the row. The first indicates the row, and the second indicates the column where the element is located. To simplify this notation, we can also note it by a capital letter. Normally, or in this other way, A sub ij. Those 3 annotations, 1, 2, and 3, will represent matrices of size m times n, whatever. For example, here we have a matrix of size 3 rows, 4 columns. Here we have a matrix of size 3 times 3, 3 rows, 3 columns. Here we have a matrix of size 1 row and 3 columns, which we will also call vector. And here we have another matrix that has 3 rows and only 1 column. As you can see, there are matrices of many types. Well, let's see a little bit of what types of matrices we have. So, the first and very important is to know that 2 matrices are equal when they coincide term to term. All their elements are exactly the same, but the matrices are different. If the numbers are located in different positions, the matrices would be different. We are going to call the matrix row, or vector row, to a matrix of size 1 times n, and matrix column or vector column to a matrix of size m times 1. This one here that you have, which is used to use the vectors. We are going to call the null matrix to a matrix whose elements are all 0. For example, this is a null matrix of size 2 rows, 3 columns. And normally we will denote it with a capital O. All the elements, all its entries are 0. Another important type of matrix is the transpose of a matrix. The transpose of a matrix A is obtained by interchanging the rows by the columns in the matrix A. I mean, if I have this matrix A that has 3 rows and 4 columns, if I want to build its transposes, I simply have to put the first row as the first column, the second row as the second column, and the third row as the third column, which is going to have 4 rows and 3 columns. That is what we call the transposed matrix of a matrix A. We can also define the opposite matrix, which is simply to change each element by opposite. That is, instead of 2, I will put minus 2, instead of 3, minus 3. Normally, it is usually denoted if the matrix A is there, as minus A, where each one of the elements is changed by sign. It is replaced by its opposite. In a special class of matrices, very important, are the ones we call the square matrices, which are matrices that have exactly the same number of rows as columns. Then, it is usually denoted only in order n matrix, not matrix n times n, for not repeating. For example, this is a matrix 3 times 3, 3 rows, 3 columns, order 3 matrix, 3 squares. And within the square matrices, it is usually talked about what we call the main diagonal. this diagonal here. If this is a square, then the first diagonal that we can build. We can also talk about the secondary diagonal, which is the other diagonal that we would build. And within the square matrices, once we know what the main diagonal is and the secondary diagonal, then it is within the matrix that is strictly diagonal. That is, it is not a square matrix that has zeros outside the main diagonal. And in the rest, it has numbers that can be zeros or not, but it only has non-null numbers in the main diagonal. A very special matrix within the diagonal matrices is the one we know as a unit matrix, or identity matrix, which is the matrix that has ones in the main diagonal and zeros outside it. This is what is called a unit matrix, or identity matrix, and it appears on many occasions in the products and in the operations that we do with matrices. We will call a symmetric matrix to a square matrix that verifies that A sub ij is equal to A sub ji. That is, it is symmetric with respect to the main diagonal. For example, here, minus 2, 5, minus 1 is the main diagonal, and as you can see, if I fold the matrix over there, they would coincide. 3 with the 3, the 1 with the 1, and the 0 with the 0. This is a symmetric matrix, since the element of the row 1, column 2 coincides with the element of the row 2, column 1. The element of its A sub ij coincides with the A sub ji axis, and we call a matrix antisymmetric to which a coincidence occurs but changing the sign. That is, I have the main diagonal minus 2 coincides with the 2 except for the sign. The 4 coincides with the minus 4 except for the sign, and the minus 5 coincides with the 5 except for the sign. That is what is called antisymmetric. Of course, since a sub ij has to be equal to minus a sub ji, that implies that in the main diagonal I must always have zeros in an antisymmetric matrix. Well, with this we have seen what a matrix is and what classes of matrices we know.